Okay, so we should get started. Hope you had a nice long weekend. Since we didn't have a lecture on Monday, so this is the first lecture of this week. And let me just first clarify a little bit. So so in this class, we have 3 lectures every week: Monday, Wednesday, Friday, usually. So but sometimes, like this week, we don't have lectures on Monday. So roughly speaking, I'm trying to have 2 synchronous lectures during the week, and the third one will be asynchronous or pre-recorded lectures. So roughly speaking, I try to keep the 2 synchronous meetings on Monday and Wednesday, and I give you some freedom to watch the recorded lectures on Friday. But sometimes, like when we don't have lectures on Monday, then we'll try to have the synchronous lectures on Wednesday. So the best way to keep up with the things is to watch for emails. So if in general, if you do not receive an email from me telling you we don't have a lecture on, like say, on Friday, then we're going to have synchronous lectures, okay? So just by default, assume that we are going to have synchronous lectures. And but from time to time, we do not have those. And then I'm going to send out the email to you, okay? So, so enough housekeeping. Let's get started. Let me share my screen. Okay. Can you see my screen?
Yes, I see it.
Okay, great. And by the way, so when I share my screen on my iPad, when I write on the iPad, I cannot see the chat window anymore. So if you have any questions, or if you want to answer some of my questions, be much better if you can unmute yourself and speak. Okay. Okay, so let's get started. So now from this week, we're going to get into the real stuff of quantum mechanics. So I'm planning to cover 2 topics this week. The first one is the well-known wave-particle duality. So in quantum mechanics, or in the atomic world, a particle is not only a classical particle anymore, they show some wave behavior. And the wave is not a classical wave anymore, they also show particle behavior. So how do we reconcile the two and understand a particle that has the wave properties, or vice versa, a wave that also has a particle property? So this is what we know as a wave-particle duality. The second topic I'm going to cover this week is the formulation of the Schrodinger equation. So more in physics, you know that we cannot really prove anything is correct. We can only prove it's wrong. So in certain sense, we cannot really derive quantum mechanics. We cannot derive the Schrodinger equation. But on the other hand, I can give you some rationales how Schrodinger himself formulated the equation that way. Okay, so let's get started. So the first topic is wave-particle duality. Okay. So as you could have seen from the pre-recorded lectures, so we talk about the 4 incremental facts that cannot be explained by classical physics. And last time during our discussion session, we also talked about a lot of other things that cannot be explained by classical physics. So just to quickly summarize, so this kind of phenomenon have 2 aspects. The first one is what we thought to be like a wave, like classical wave, for example, photon or light. So classical physics told us light is nothing but an electromagnetic wave with certain wavelengths. So it is a wave. But when we go to the high energies of light or short wavelengths of light, so the behavior of light behaves more like a particle. So what we thought as a wave behaves more like a particle. So largely this is related to high frequency waves like X-rays or gamma rays. And when they interact with matter, we have to assume proposed by Planck from the very beginning. So the energy of the light, it has nothing to do with the amplitude of the wave. Rather, the energy is only proportional to the frequency or angular frequency of the light. Okay. So with that assumption, we're able to explain phenomena like the black body radiation, photoelectric effect, Compton scattering, etc. Okay. So, but this particle is not a classical particle. And Einstein used the word photon to describe this light particle. So that is one part of the story. What we thought to be a wave now behaves more like a particle. So the second aspect is for classical particles, for example, electron. When I put an electron inside the atom, it's confined in a small space. So their behavior is not particles anymore. So for example, just think about a hydrogen atom as example. A proton, that's the nucleus, and the electron going around the proton in the classical way. If that is the case, then we wouldn't have a stable atomic model. So rotating electron is going to give out electromagnetic radiations and lose energy. And very soon, the electron is going to collapse into the proton. Okay, so in Bohr's hydrogen model, he assumed that the electron's behavior is not like a classical particle going around a circle. So instead, the electron occupies certain tracks. Later on, it's called orbitals. And we don't, at the time, at Bohr's time, he didn't really understand what this kind of orbitals look like. But rather, he assumed that if the electron occupies that orbital, then it doesn't give out electromagnetic radiation, okay, which is against the classical physics. But only through this assumption, then we're able to describe the behavior of the hydrogen atom. So when we put the electron in these orbitals, then these orbitals must satisfy certain conditions, namely the wavelengths of this electron. Now we have to talk about the wavelengths of the electron. Will be integer multiples. No. So actually, the circumference of those orbitals will be multiple integer multiples of the wavelengths. So you know a little bit more what I am saying when we try to solve the behavior of electrons inside the hydrogen. So the bottom line is the behavior of electron is not a particle anymore. So they behave more like a wave. So instead of I can draw a picture here. Instead of electron going around, so like an electron going around the proton, it's more like a electron itself is completely delocalized. So we still have these orbitals, but we cannot pinpoint the electron on the track. So instead, the electron behavior is more like a standing wave. Okay, it's more like a standing wave on these orbitals. Okay. So, in other words, the behavior of particles now became like a wave. And we can see that again and again in the future. But basically, these are the two ingredients that leads to quantum mechanics. So the classical wave now behaves more like a particle. At the same time, particle behaves like a wave. So for any atomic subatomic particle, they have these two properties at the same time. So they can be considered as both a particle and a wave. In fact, this is what the terminology, the word quantum comes from. So, so in quantum mechanics, everything is so-called quantized, or described as this quanta. Okay, so quantum means it's a portion of a discrete energy. So not only the wave, not only for example, the wave becomes discrete, become particle, but also the energy changes from continuous distribution to a few discrete type. So with what we thought to be continuous, so in classical physics, everything is continuous. So now it becomes discrete. So this sort of a discretization leads to quantum mechanics. This discrete behavior is called quantum. Okay. So now how do we formulate the new physics to describe the behavior of fundamental particles? Then, so that is the focus of the theoretical development at the beginning of the 20th century. So before the 20th century was the classical physics, from classical mechanics, classical E&M, to classical statistical thermodynamics, all of the classical physics. And so the year of 1900, roughly, is the beginning of the modern physics. So in fact, the year of 1901 is exactly the first year when the Nobel Prize was given. And the first Nobel Prize was given to the discovery of X-ray by Röntgen. So then when these new phenomena were discovered at the time, it's apparent that we need to develop a new physics. And at the time, nobody knew this physics is going to completely revolutionize how we view the world, okay, how we look at the universe. And this is what I'm going to teach you in this class. How do we look at the world with the quantum mechanics perspective, especially in the nuclear and atomic phenomena? Okay, so a lot of the pioneers and the giants in physics made important contributions to the development of physics. And to get things started, first we have to solve this puzzle of so-called wave-particle duality. So how can a wave be a particle at the same time? And so take a classical particle as the example. Let's say electron. If an electron is moving with certain energy and momentum, then if you are saying the electron also has a wave property, then what is the wavelength? Okay, so the first contribution is made by de Broglie. So he actually took the simple equation proposed by Planck. So Planck assumed that the energy of the photon, E, is proportional to its angular frequency, h bar omega. So h bar is the reduced Planck constant, is the Planck constant divided by 2 pi. And omega is the angular frequency of the light or photon. Okay, so at the beginning, he only used this for photon, but it turned out that this is true for all the massless particles. The most common massless particle is a photon. So oftentimes for photons, we write down E is equal to h bar omega. And it didn't take long for Einstein to figure out that this is not only an I-thought assumption, it is the true physics, and he gave the name photon. So so this equation is the first part that links the energy of a particle. The left-hand side could be the energy of the particle, and right-hand side is the frequency. Okay? It's the wave properties. And when de Broglie did his PhD in the early 20th century, well, he knew this equation, and but he took it a little bit further. He assumed that not only the energy related to frequency, but also the momentum of a particle is related to wave properties, so a momentum p. And we know that in order to describe the behavior particle, we need both of them. So only the energy is not enough. We also need to know the momentum, so E and P. So E is already known, is related to h bar omega. What about momentum? So de Broglie proposed that the momentum of the particle is also proportional to the Planck constant h bar. Okay, but it's equal to h bar times k. Okay, so k is a vector. In fact, the k is called the wave vector. So k is a wave vector. So I'm only writing down the magnitude of k. So k is the vector, wave vector, and it's defined by 2 pi over the wavelength of the wave. It's called the wave vector. So when we describe a wave, then we have a wavelength lambda, and wave vector k is the 2 pi over lambda, and the direction is along the direction of the propagation of the wave. Okay. So then, well, you can rewrite this a little bit. So h bar, if you only let's only write down the magnitude. So p is h bar, it's h divided by 2 pi, and k is 2 pi over lambda, so 2 pi cancels out. So another way of writing down this formula is momentum equal to h, the Planck constant, divided by the wavelength. Okay. So so this is in fact, this is the original equation de Broglie proposed, and this kind of wavelength is called the matter wave. So for any matter, like a fundamental particle, electrons or protons, and can also be even as heavy as us, like a human. So we have, if we are moving, we have a momentum. Then if you use h, the Planck constant, to divide the momentum, we get the wavelength. Okay, so any object, any particle can also have associated wavelengths. Okay, so and because of the Planck constant is a small number, then the typical wavelength for macroscopic object is actually very, very small. And we don't really see the wave behavior of a macroscopic object. But when the momentum is small, for small particles, then the wavelength becomes much larger and become a important effect. Okay. So when de Broglie proposed that, this was the beginning of 20th century, and there wasn't any proof. And essentially, this is the equation, the second equation. The first one is already known. So the second one is the center part of his PhD thesis. Okay. So later on, this was proven again and again. This is correct. So for any fundamental particles with the momentum, then you can compute the wavelengths easily this way. And with the wavelengths, then you can describe their wave properties. For example, one of the well-known wave properties is interference. So there are many kind of interference. Like for classical wave, then we know if you send a wave and split the wave into two and pass the wave through two slits, then we can have interference pattern. Okay. So, and this suggests that even classical particles like electron beams, if you can split the beam then into two, pass them through a double slit, and those classical particles can also have interference patterns. So in other words, they're not waves anymore, they're not particles anymore, they also have the wave properties. So, But at that time, it was very hard for people to accept. How can you say a particle is also a wave? And but conceptually, it is a true revolution. After all of those concepts were verified later on, and the Broglie won the Nobel Prize in 1929. Okay, in fact, when he won the Nobel Prize, he was only 32 years old. He was only 32 years old. So, and during his PhD defense, and no one really understand what he was saying, and no one accepted that. I mean, it's easy to understand, but it's difficult to accept. How can a particle has a wavelength? Okay, so what is the nature of the wave? So, so the rumor was that his thesis was only it's only 1 page long, only has this one equation: P is equal to h divided by lambda. So, but actually that is not true. I checked his PhD thesis, so it's actually much longer. So although it's not as long as the PhD thesis nowadays, a typical PhD thesis will have more than 100 pages, maybe a minimum 100 pages. His thesis is not that long, but still not 1 page. So, although the essential components can be put down in 1 page, P equal to h divided by lambda. But Einstein actually was on his PhD committee, and Einstein knew the significance. That's why the Broglie passed the PhD defense and got his PhD. So, well, nowadays when we use the Broglie equations, it's more often we use P equal to h bar k. We use this wave vector much more often than the wavelength. But wave vector is nothing but just inverse of the wavelength. So it has a dimension of the inverse length scale is 2 pi over lambda. So if wavelength, let's say for atomic distances is angstrom, then the K is usually has the unit of inverse angstrom. So let's say if the wavelength, we use the dimension unit of angstroms, wave vector K usually has the dimension of inverse angstrom. Or if wavelength we use nanometer, then the K has the inverse nanometer. So, for example, if you ever run a X-ray experiment, X-ray diffraction experiment, then the x-axis you usually put into this inverse angstrom or inverse nanometer. For X-ray is more often to have the unit of inverse nanometer. So there's a wave vector, and momentum is just proportional to the wave vector. So if we look at these two equations at the same time, the left-hand side describes the quantity usually associated to the classical phenomena, energy and momentum. You can associate the energy and momentum to the motions of a particle. And right-hand side are usually the quantities we describe the wave, like the frequency, omega. In fact, omega is the angular frequency. So omega is 2 pi. So omega is the angular frequency. Is 2 pi times so-called frequency. So now you can also see the symmetries between these two. So omega is 2 pi times frequency, and K is equal to 2 pi over lambda. Okay. So if we combine the two together, so omega, so for example, for light, so omega is cancel frequency, so it's a CK. Omega is equal to CK, right? Frequency, or in other words, C, the speed of the light. So omega is equal to CK, or if you use a frequency, or like say C, there are many ways that we can manipulate this simple formula. So C will be equal to omega divided by K. So we can also change this omega and K into frequency and wavelength. So omega, okay. So omega is 2 pi f, and k is 2 pi over lambda. So 2 pi cancels out, so c equal to lambda times frequency. Okay? So that might be the familiar, this is an example, the familiar equation that you have for light. So speed of the light is equal to the wavelength of light times the frequency. Right? So the frequency is how many vibrations in the way you have with 1 unit second. And this number of these vibrations, the entire period of wave times the wavelength will give you how far the wave travels within unit time. So c is equal to lambda f. So actually we use all of them pretty often. Omega equal to ck, or c equal to, let me change a different color. Omega to ck, and c is equal to omega divided by k, or c equal to lambda f. So in quantum mechanics, we use the angular frequency and the wave vector k much more often than direct wavelength or outer frequency. So that's why this left-hand side are more often used, and the omega and k are nothing but the wave properties related to frequency and the wavelength. Okay. So then with this, if you take a classical particle from the left-hand side of the equation, if we know the energy and if we know the momentum, then we can easily get the angular frequency in the wave vector by dividing out the h bar. Then we have both of them. When we have the omega and k, then we can write down the so-called wave function. So wave function. And the wave function, we usually use this symbol, Greek symbol, psi or psi, depending on where you're from. So the pronunciations is slightly different. So I usually call it psi. The psi as a function of real space, r and t. Okay. So we want to describe a wave, we want to know the wave at a certain time at a certain location. And so in amplitude, it is psi naught. And when we know the wave vector k and the frequency omega, then we write it down this way. So e to the I k dot r minus omega t. Okay. So to make it more obvious, so let's say if it's one-dimensional wave, so x at t is one-dimensional, then the amplitude still here, and the k becomes k becomes only along. So if you describe a wave propagating along the x direction. Okay, height means the unit vector along the x direction. Then k becomes a scalar. So in this case, k dot r would be k along x direction times x. So just k x minus omega t. Okay. So a more common form you might be familiar with is, instead of using this imaginary part, using complex number. So you have seen either cosine and cosine. Here we have both the cosine terms, the cosine kx minus omega t. This might be a more familiar form of the wave, or psi naught times the sine kx minus omega t. Okay. And combine both of them together, then we have the exponential form. Okay, so even classical physics, sometimes we use this cosine sine form, sometimes we use these complex numbers. So in fact, for standing wave, we usually only use the real form, but for propagating wave, we use the exponential to the imaginary number e to the I kx minus omega t. Okay, so this is the simplest form of the wave function It travels from minus infinity to plus infinity. Okay. And the wavelength is lambda, so the wave vector is k. And the energy of this wave is h bar times omega. Okay, so this is a simple wave function for plane wave. Then the question coming after that is, for a particular system we're interested in, for example, the behavior of electron inside the atom, then what is the wave function? Okay, in fact, there are two questions immediately coming from this interpretation of wave particle duality. So number one is given a particle, or in the classical sense, given a particle like electron, how do we find out the wave function? So there won't be the simple free wave function form. Okay. So this is the only function that travels a plane wave, travels from minus infinity to infinity. When we put a particle in an atom, what do I mean by inside the atom? You see, if the particle is interacting with something else, so like electrons interacting with a proton, then what is the wave function? So the question number one we need to solve is, how do we find out the wave function? What is the differential equation that governs the behavior of the wave function? And that's part one of well, this question one of the entire quantum mechanics. And the second question is, after solving like certain differential equations, we're able to find out the wave function, let's say for this electron. Then how do we know the energy or the momentum or any properties associated with this particle? So let me write down these two questions. So the first question is, how do we determine the wave function? Okay. So the second question is, given the wave function, then how do we determine the properties of the particle, like energy and momentum, and even the basic one, the location of the particle. Okay. So in fact, these two are closely related to each other, and this will be the topic of formulating the sorting equation. So we'll do that next time. So but before going that far, let me mention a few things about this wave particle duality. So it is really hard to understand, and this is what I mentioned, why the pioneers of quantum mechanics well, I'm going to give you two quotes. So one is from, So one is from Bohr himself. The Bohr said, if you are not confused by quantum mechanics, you haven't really understood it. Okay. And second quote is Richard Feynman. He said, I think I can safely say that nobody understands quantum mechanics. The quantum mechanics is a difficult subject in two senses. One is the concepts are very, in a way, very weird. So they're nothing like the classical physics. So then in those cases, you always have some classical object that you can compare with. But quantum mechanics, the first one, like here we talk about wave particle duality, doesn't really have a classical counterpart. In classical physics, a wave is a wave, a particle is a particle. Okay, they are described by completely different things. So for the particle behavior, then if we for particle or object, we can define the energy momentum based on their trajectory, meaning the location of the particle at certain time, and take derivative, get the speed. So you have to know the location of the particle and how to know the speed. For classical wave, we describe them by the wavelengths and frequency. So like the right-hand side of these two of equation. Okay. But in quantum mechanics, these two are closely related to each other. In fact, they are the same. So a particle also has a wave property, which is hard to understand. This is why even the pioneers said that we don't fully understand quantum mechanics. So second part that makes quantum mechanics difficult is very soon we're going to, well, since you already seen, we have introduced this complex number. The complex number is needed in the wave function. So we have to formulate a partial differential equation that involves an imaginary number, that involves complex numbers. And only by solving that differential equation, we're able to find out the wave functions. So to solve this question number one, how do we find out the wave functions? And the second, from given the wave functions, we want to find out the properties. And then, so here that involves multiple steps. First step is we can use calculus to do this, but later on we'll see that it's not a easy way to understand the properties. And then we're going to project those wave functions into a high dimensional space, so-called Hilbert space. And then in this high dimensional linear space, we're able to understand the solutions of the differential equations much easier. Okay. So the second challenging part is the math. Yes. So these two things together, obviously the subject is not going to be easy. We're introducing new concepts. Really, maybe in a way, the very new concept, nothing like all the other courses you have taken. And second is we also have to introduce a lot of new math to describe. So those made the quantum mechanics difficult to understand. And that comes back to another topic, like what do we mean by understanding? So this is a long conversation. I can spend hours to talk about what do we mean by understand. Okay. So in short, we don't really understand anything. So we just get used to it. So the level of understanding really depends on the computational complexity and accuracy. So if you ask the question, like, do we understand quantum mechanics? Do we understand this particle wave duality? Then I can tell you we don't. Okay. But the question is can we make rigorous calculations and predict the properties of the subatomic particle? Then the answer is yes. So we can use accurate differential equations to find out the behaviors exactly. So in that sense, we understand quantum mechanics. Okay. So in usually, even classical physics, when we learn something new, so what do we mean by understand it? And usually the teacher will give you some sort of comparison to maybe a daily phenomena. For instance, what do you mean by gravity? How do you understand gravity? And if we say gravity means like any two objects will be attracted to each other, you say, okay, I don't understand that. But on the other hand, let me give you an example. So like the apples are going to fall to the earth instead of flying to the sky, and that is due to gravity. And you say, okay, now I understand it. Apple falls to the ground. But that doesn't really add anything new if you think a little bit more. So the reason that now you feel that you understand it is because of now you can understand this simple gravity equation with the phenomena you already know. Okay? So if the phenomena does have a classical counterpart, then we can use that to explain the theory. But in quantum mechanics, the problem is we don't. The classical world doesn't behave like this way. So like we don't have a classical wave-particle duality. In fact, the phenomenon is still there, but the effect is so small, it's completely negligible. So, going back here, so how do we understand this wave-particle duality? You might be able to find lots of explanations from the internet. They try to explain what do we mean by wave, and in a way, throughout the semester, you will gain some sort of understanding. The wavelength, the wave function will be used to describe the probability distribution function. In fact, the square of that will give you the probability distribution function that tells you where the particle can be found. Okay, so the meaning of the wave is probability. Okay, so but only that at this stage, if you introduce more, it only adds you more confusions. So let's leave those aside in a little bit. what I want to emphasize is that the wave properties of the fundamental particles are really observed again and again and again from all sorts of experiments. So it is those experiments that made us confident about this assumption. Okay. So it's not obtained through like logical reasonings. So physics is an experimental subject. So all the theories we build are based on those solid experiments, and we can test if those theories are correct or wrong by comparing the predictional theories against the experiments. Okay. So let me give you a few examples here. So let's take an electron again. Let's take an electron as the example. So if we are saying electrons are not only particles anymore in quantum mechanics, they're also waves, then they need to have the wave properties. So in other words, if we send like a beam of electron and split them into two, okay? Then if you pass these two through a classical double slit experiment, if they are particles, then each of these beams are just going to continue with their track, and you can only detect these particles at these two spots, okay, on the detector. So this is the classical scenario. So quantum mechanics is correct. And then what's going to happen is those particles, those beams of electrons are also waves. They're more like waves. So the wave, when pass two waves through the two double slit, they're going to interfere with each other and depend on their phase. So what you see is not only two bright spots on the detector, but rather you have these stripes. So like near the center, just draw here, near the center of the detector, we're going to see a peak. If for classical particles, we're not going to see, like, see the electrons like classical light. If you put your eye here, we won't be able to see anything. But if we pass a wave, when this wave interact with each other, we see those stripes. Okay. So in fact, that was the one of the first experiments that made us to believe like light is a wave. So now, if electrons are also waves, then this is okay. This is quantum behavior. And this provides us an experiment for us to test whether electron is a wave or a particle. So, and the experiments were exactly done near the beginning of the 20th century by Thomson. So this is not the Thomson, the J.J. Thomson that discovered the electron. This is his son. So there are a few son, father who won Nobel Prize. This is one of them. So this is the son of J.J. Thomson. So he exactly did the experiment and discovered that indeed the electrons will interfere with each other and generate this pattern. And this is beginning of the electron diffraction. Okay. And for this work, so Thomson and Davidson. So Davidson won the Nobel Prize. So Davidson, Thomson won the Nobel Prize. But Davidson did experiments with Germer. Germer didn't win the Nobel Prize. So Thomson and Davidson won the Nobel Prize in 1937 by precisely show the wave behavior of the electron. Okay, so there will be a lot of philosophical thought put into that, like how come electron behave like a wave? So throughout the semester, we'll come back to this classical example multiple times. Okay. So so now we know like electron is not only a particle, but it's also a wave. And we make use of these properties all the time. For example, even in our campus, we have multiple electron microscope. So microscope is we use light to see things. Now we can also, since electron is a wave, we can also use electrons to see things. And the advantage of doing that is we can compute the wavelengths. Right? We can compute the wavelengths based on the equation shown here. If we know the momentum, we know the wavelengths. For electron, the wavelengths turn out to be very, very small. And that allows us to see small things. So for example, for the energy of an electron to be 10 keV, okay, kilo electron volts, and the wavelength is 0.122 angstrom. So the size of atom is usually measured in terms of angstrom. If you want to see atoms, then we need a wave to be in the range of like at least angstrom or sub-angstrom. So electrons with 10 keV, we can easily accelerate electron to 10 keV. And then the wavelength becomes like 0.1 angstrom, perfect for us to see the structural atoms. And that's why we do use electron microscope to all kind of electron microscope, scanning electron microscope, transmission electron microscope, all of them, to see the atomic structure of materials, all kind of materials, even living objects. So, and the other thing we can use, so this is the electron. I'm talking about angstrom. We can also use X-rays, right? We can use X-rays. So for X-ray, typical energy of X-ray, let's say if it's generated by copper K alpha. So K alpha is a transition of the 2p electron to 1 IC electron. You learn all of this throughout this semester. So during the transition, give out the X-ray, the wavelength is 1.15418 angstrom. Okay, and energy of this X-ray is about 8 keV. So we can also see atoms and molecules with X-ray, like with light, high energy light, 8 keV, way beyond the visible light range. So visible light is 1.5 to 3 electron volts in the range of electron volts. So if you increase energy by 1,000 times, then the wavelengths become much shorter. So now it falls into angstrom range. So we can also use X-rays to see atoms. Okay. So, and this is to make use of their wave properties. And of course, X-rays, there are a couple of Nobel Prizes associated to X-ray. The discovery of the X-ray was the very first Nobel Prize given by Röntgen. It's 1901. And this particular X-ray diffraction experiment. So there were 2 Nobel Prizes. One is Loy, one Nobel Prize in 1914, and then the so-called Bragg scattering. So Bragg, so this is another pair of son and father. So Bragg and Bragg won the Nobel Prize in 1915, also by developing this X-ray diffraction experiment. And nowadays we use them to study material properties all the time. Okay, so the X-ray is kind of known because we accept that X-ray is a wave. Right? So, and now you can also do the same thing with the electron. Okay, so in fact, not only electrons, X-rays, you can use all fundamental particles as a wave to see things. Okay, so and to think about another way, so X-rays has much higher penetration power than electron because electrons are charged. They're also repelled by the positive nucleus, so Coulomb interaction. So electrons cannot go inside the materials very deep. If we want to go inside materials very deep, then we can use a neutral particle. So for example, neutron. So this is why we care about this in our department. So with neutrons, we can do the same thing. So okay, so let's say neutron scattering. So let's say we generate the neutrons from nuclear reaction. Let's say either a fission process or spallation process, and then the energy, of course, is very high. The energy of neutrons is very high, but we can cool them down. We can cool them down. We can bring them down to room temperature, to thermal neutron. So what is the energy of thermal neutron? If there's one number that you need to remember in this department, that is the energy of thermal neutron. It's 25 milli electron volts. It's very small energy. So the reason it's called thermal neutron is you can equilibrate the neutrons with room temperature. So temperature is 300 K. So follows Boltzmann distributions at 300 K, get energy is 25 millielectron-volts. And the speed is also important number you need to remember is this 2200 meters per second. Okay, it's pretty fast. Now with the energy, okay, you can compute the velocity, what the speed is here, the momentum is here. Then you can find out the wavelength of the neutron. The wavelength of thermal neutron is 1.8 angstrom. Okay, so you can also use this 1.8 angstrom neutron to see things, and by sending beams of neutrons through materials, and it's exactly the same way as use X-rays to do diffraction experiment, and as the electrons you can do the diffraction experiment, and then you'll be able to see things with neutrons. And there are a lot of advantages of using neutrons. One of them is they're neutral, they don't have charge. So we know neutrons can go very deeply inside materials. So you're not confined to only study the surface properties. So there are many other advantages. So one thing I want to point out here, if you look at the wave, it's not only the wavelength is close to atomic distance, but also the energy of the neutrons is millielectron-volts. This is related to the time scale of the motions of atoms. So atoms are usually vibrating inside the solid materials, or diffusion, like in a liquid, like in fluid mechanics. And the time scale is right at this millielectron range. But with neutrons, not only we can take a picture of where the atoms are, but we can also take movies, how they move. And this is the one important applications of nuclear engineering, neutron scattering. In fact, this is what we do in our group all the time. And this work was given the Nobel Prize much later than the electron X-rays. So the Nobel Prize was given to Cliff Shaw and Brockhaus much later in the 1994. Okay, so, and because of neutrons, intense neutron beams much harder to generate. And nowadays have two ways to do that. One is through a fission, so nuclear reactor. And second is through a spallation source. So both of them were only developed much later in the 20th century. Okay. So the Nobel Prize was given much later. But on the other hand, neutrons are just like the other particles. They have wave properties, and they can use the wave properties to do diffraction, to do imaging. And wavelengths can be easily computed with the de Broglie equation. Okay. So in fact, before moving to Illinois, my position at Oak Ridge National Lab is it's called the Shaw Fellow. It's named after him, Shaw. And Brockhaus, interestingly, is my PhD advisor's advisor. Okay. So by that, let me. It's already 9:55. Let me just stop here today. And so this lecture is about wave particle duality. And on Friday, we'll come back and talk about the Schrodinger equation. Okay. Thank you very much, everyone.
Thank you too.
Thank you, Professor.